This is a three-dimensional LiDAR. This little guy is able to see objects as far as 40 meters with a precision as high as 2 centimeters. And this one is a sensor called Mid-360. And the name is obviously because it's a 360 sensor. It was developed by a company called Livox. And Livox is a company that started inside DJI. And nowadays it's a company that sells cost-effective LiDAR sensors, which was a good thing in the end because LiDARs, especially three-dimensional LiDARs, are typically expensive in the market. Today, we have a mission. We were hired by a company that is developing an innovative computer vision system for autonomous cars. Our mission is to develop a highly efficient LiDAR sensor driver that has to run in a Raspberry Pi via a container, and a computer vision specialist has to consume that LiDAR data in his environment. And that computer vision specialist is gonna use the LiDAR data to run his localization and mapping algorithm. However, he is not a C++ programmer because he is a Python engineer who has his frameworks and technologies and AI tools, TensorFlow, PyTorch, everything was written in Python. So somehow he has to use that Python environment to collect the data from your sensor driver that was written in C++. And on top of that, the environment where he's supposed to run the SLAM algorithm is not a Raspberry Pi. It's a different device that is a GPU embedded edge computing device. So he has to retrieve your data remotely, somehow. Where do I even start from? Don't worry, I got you. Today you learn how to write a gRPC server that is capable of streaming LiDAR data in real time. You're gonna learn how to use CMAKE to produce binaries such that you can put them inside a standalone container that you can just literally import in a Raspberry Pi. We're also gonna learn how to import and deploy those containers in the Raspberry Pi. And finally, I'm gonna show you how to write your Python script that is gonna consume that LiDAR streaming interface via gRPC. Now, let's be fair. ROS, which stands for Robotic Operating System, would be quite a suitable choice. If we would write our LiDAR driver as a ROS node, we could use it to publish the LiDAR data to a topic, and then the CV engineer could write his Python script, subscribe to that node, consume the data, and we're done. The only downside of using ROS is the fact that you have to really learn about the technology, so you have to learn all the concepts, nodes, nodelets, topics, publishing, subscribing, emment, build system, transform messages, message definitions, DDS, compositions, and that can be a little bit overwhelming. Sometimes we just start using ROS because everyone else is already using ROS and they all have the good use cases to come up with reasons to use ROS. But sometimes we just take things for granted, not really understanding what we truly need. But today, we're gonna keep it simple. It is a very good idea at the beginning of a project like this that we draw something that describes our ideas. Mainly because we often want to discuss about the ideas with the stakeholders and we want to see match expectations and we want to see if our idea makes sense. And by putting your ideas, the description of your components, interfaces, relationships in a drawing board or a diagram, you can easily point your ideas to things you can actually work on or change. And also very important to realize is that whenever there is an interface involved, meaning that someone else is gonna consume something that you're gonna implement, interfaces are typically a good starting point because then you can leave the details for, let's say, the lower level chains of development. But the interface is what establishes the services and the data, and that's definitely something you can start with. So if we look at this diagram, which has the complete view, but for starters, let's imagine we don't have anything, but we're trying to come up with an interface. So here we have two deployment environments. We have the Edge GPU, which is running the Python environment, and all the AI stuff for SLAM, and on the left side we have the Raspberry Pi. So by using the proto file to derive the services, we are effectively solving a big part of the problem that involves discussions. If we come up with a proposition, hey, this is the services that I can offer, this is the data type stream to your client, if your engineer already agrees with this and you use a gRPC and a proto define and discuss about the interface, you're almost halfway done, because the code involving networking and are going to be generated for you automatically just by using gRPC. So what kind of proto file can we use to establish our driver interface? It could be something like this. So we can think about the services as a driver server. Let's put it like this. I think we can keep it simple, and we can create an RPC called getScan. And this is where gRPC shines, because it allows us to stream data, meaning that we keep the connection alive. The client keeps listening as new data comes real fast. So there's nothing in the networking required to establish new connections, new handshakes. No, the connection keeps alive. The data just comes from the server towards the client, and you're getting the data as the driver is fetching from the actual sensor. So this is how we define this in gRPC. We put this thing called stream, and here we also define the data type. And in that case, it's quite simple. The point cloud is a collection of points. So we say repeated points. Optionally, the server can set a timestamp to indicate when was the point cloud sampled, and each point cloud is a collection of points. So this means that the point is Cartesian points, three-dimensional XYZ, and depending on the driver, we can keep it generic. The driver is also, in case it detects color somehow, it's also possible for the driver to set these fields, and the server can set these fields, and the client can understand, oh, okay, this kind of sensor driver has a color setting, for example. There are better ways to do this, but just for the sake of showing you that we can keep an interface generic enough that we can think about future cases or different kinds of sensor drivers, LiDAR drivers. Another important field is intensity. So LiDARs typically have some sort of intensity, so how strong your signal came from the object. It is also something that some LiDARs are able to detect. Once more, we can set this as an optional field to indicate if the driver supports that, it's going to set that field for you. The reason why I like gRPC so much is because it stimulates you into thinking about interfaces. Interfaces are often biggest points of discussion between stakeholders. And over time, in my experience, I've really learned that interface, data, services are very common points to generate discussions and often sources of problems. And using gRPC, not only we try to approach those discussion points as a service definition file, the service definition file actually generates the code for you. So your services are implemented and generated automatically for you in multiple languages, such that they can even, multiple different languages can call your code or your server. Really helps you tackle problems that might involve multidisciplinary people. So some people are specialists in TypeScript for rendering point clouds in the web. Some people are specialists in Python for using AI. Some people are specialists in sensory drivers like C or C++ engineers. And I like a lot gRPC because it offers you a bridge to unite all those different languages with a single service definition file. All right, so we know everything about the services. We have a service definition file. We generate Python code in the Edge GPU side, and we generate C++ code in this Raspberry server side. And here is the generated code by gRPC, which is effectively bridging the communications between those two devices via a definition file. The way to effectively bridge those objects, the service and my physical sensor, is of course using an interface, which is described by this LiDAR interface. It literally decouples. It doesn't care about the implementation, particular implementation of this sensor. As long as it uses an agreed interface to communicate with your concrete implementation, you're effectively a little bit future-proof. So in case the new drivers versions are released, or in case we want to support different drivers, different types of sensor like this one, just all I have to do is inherit this LiDAR interface, create the implementation with all the details needed, and pass as a pointer or as a virtual class. We just pass the reference to our gRPC publisher, which doesn't care about the details. It just cares about the functions and the data type that it's going to expect from that function calls returns. And here a little bit to the left, here we have a definition of what the point is and a definition of the scan3D basically just stating our data types. This is important because scan3d is a data type that is going to be passed all the way in all chains of dependency all the way to the service. And there has to be some kind of translation between the low level point tree that is being fetched from your lower level driver sensor to the proto definition of that point. Now that we have a good idea on the overview of our solution, we can start discussing the details. For example, how am I gonna implement a library around this particular sensor? Typical workflow that one can do is to browse the sensor vendor, look for the details, look for manuals, look for specifications, look for downloads. And in the case of Me360, this is a very nice page, by the way. It shows high-level details and specifications of your sensor and all the inner workings of it. It's a cool animation, how it works. It's a solid-state driver. It shoots lasers in that particular pattern. It has a good amount of field of view, and you can, search for yourself. So if you browse the vendor page, eventually you're gonna find an SDK or library. And here you're gonna see what he offers. For example, for Me360, we could have used either this one or the actual Livox for us 2 driver. So in my case, I'm gonna go for this one, and this turns out to be a repository. And here it tells us how to build it. It's a CMAKE project, so we can easily integrate that into our application. That's what we need to know. And the way we integrate this into our repository is by adding the Livox SDK2 as a submodule, for example, to our application, to our repository. And here all the vendor stuff is added automatically. Looking back at that picture, we see here a gRPC publisher. In the case of this sensor, Me360, I've created a dedicated application called Me360 Publisher. And this is the actual binary or application or program that's going to be run in the Raspberry Pi in the form of a container. So this is the callable executable by your means. And here is how we use it. So here we instantiate our LiDAR driver object. This is the actual thing that implements this guy. And we see here that it inherits our iLiDAR interface, and our iLiDAR interface is a abstract interface class in C++. So there's nothing, no functionality whatsoever, just the agreement of what this interface can look like for any kind of sensor. And here, of course, you also define the types. So our whatever driver we develop, whatever library we develop that inherits this interface has to honor that data type as a return type. All right, the Me360 is the class that inherits this, implements all the functionality. It has a queue internally, and looking at the C++CC file. So this is what actually calls and really depends on the vendor library. This comes from the vendor. This also comes from the vendor. All the details on the vendor specific things are inside this C module. And here we call, this is the SDK provided functionality that grants me access to the driver. What matters from this file is to understand that this is me creating a high-level object, Me360, that gives me access to my LiDAR device, that implements a generic interface, and the details are internal to that module. That's what matters here. Going back to the publisher application, we instantiate the LiDAR, we initialize it, and there's a few small configurations done. Start the sampling. After this point, the sensor library is activated and probably already getting samples from the sensor and storing those samples in the memory of the driver. And this is where we start the server. So the server is a class that I created that contains the service. So the server is something that is up. So it starts, it listens for connections, and one of the attributes of the server is the actual service. And the actual service is the gRPC generated class This is gRPC, and this service is our implementation of the protobuf generated gRPC code. All right, so those are, gRPC offers us virtual classes. All we have to do is inherit the service generated by the proto, and then we implement the actual functions. So in that case, getScan, which is something that the client is calling, so that's why it's called getScan from the perspective of the caller, of the user of the service. It's a getScan. So the client is calling getScan, and the implementation of that getScan in my server side is quite simple. It's literally, if there is a connection attempt, until I have sensor data in a queue, send this to the client. Keep sending the point clouds to the client. If my driver puts new sensor data in the low level, it put in the queue, and then the server access the queue, pop the queue, sent over the wire to the client. It's quite simple. It's just a queue, and that queue will be the buffer between the low-level driver and the high-level server, and the queue is gonna be the bridge, the buffer between those two parts of the application. Important thing is to understand that how the proto part works. So here, if I browse proto, this is our service definition. This is the representation of our driver as a server or service, and this CMAKE lists. It effectively looks at this proto file and generates all the necessary libraries that's going to be used by the other modules of my application. So here is a very nice function that I created. Generate proto. Generate proto. It's a function that I created that looks at the proto file, calls the proto C compiler with the right commands, and generates the files that I can use in my code, like this. Now let's see how can I wrap all this application in a single standalone dev container. Thankfully, CMAKE allows us to do exactly that. So there are ways for us to produce binaries that are absolutely self-sufficient. CMAKE install has a special attribute that you can add called runtime dependency set. And what it does is it's gonna look at your binary, it's gonna look at all the libraries that your binary depends on, and it's gonna add everything to the installation folder. The thing is, it's also gonna add system libraries. So even libc and libc++ is added at that runtime set. So this means that if I call something like this, CMAKE will build my application, and it will get all the binaries it's going to put in the installation folder. This is really useful because if we are producing a container that doesn't have any dependency, it's really simple. We can have CMAKE install dependencies together with this binary. If you don't want system libraries to be added, you can filter what libraries you want to include then. So for example, I'm aware already that the PCL is a dependency that I want to add. So like this one. Boost, I want to add boost as well. For example, for IO streams. I2C for accessing IMU device. Op. So I'm aware of exactly the libraries that my application needs that are not system libraries. The way I know that for sure is by calling LDD, Me360 publisher. Here we have a list. This is a system library. This is a system library. But every library that is not a system is added at that pre-include regex. What's important to realize is that doing this, you don't have to install your dependencies inside your container that's going to run this using some package manager. This makes your images extremely small and self-contained. And to show that, I'm gonna build this inside a container. So here I have a Docker that is gonna build my application, my CMAKE application, the server. This whole server that we've been talking about, I've produced a Docker file that is gonna build that application, and it's gonna build from a Ubuntu new image, and literally I'm just gonna copy those binaries and all those dependencies to that clean Ubuntu image, and I'm literally gonna call my application as an entry point. So I can just call it like this. There's no apt update, apt get, nothing. All the binaries and dependencies are already included like this. So if I do this, what I'm doing is I'm building this self-containing container that I can literally just copy to my Raspberry Pi, and it's gonna work. So I just finished the build. I have a new image called mid360, Docker images, mid360 created 3 minutes ago. We are good. So now I just have to do this, Docker save mid360 tar.jz. So now I have a mid360 tar.jz to send over to the Raspberry Pi. This is my Raspberry Pi. It has only Docker installed. It has no images yet. And what I'm gonna do is I'm gonna copy this mid360 to the Raspberry Pi. And it's done. This is the archive of my image. I'm just gonna have to do this. Perfect. I have a new image in my Raspberry Pi. And I'm gonna run it. Docker run mid360. And of course, my Raspberry Pi is connected to that device. Gonna do yes, network host to access the device as an Ethernet device. This is a few commands. Yes, that is expected because the sensor was turned off. I'm just turning on the sensor now. And that is expected, of course. The sensor is on. And I am ready to get some samples. This guy is spinning. Perfect. Back to our code. I've written a client in Python that does almost nothing, just fetching points. Let's call this. So if I go to this directory, go back, so the workspace test client, I do set up my Python environment, make sure my IP is the IP of my server, and here I am getting the points from my LiDAR sensor. I'm getting roughly 48,000 points every 300 milliseconds, roughly. And there you have it. I have a client in Python calling gRPC, using the same proto file and accessing every point that the LiDAR sensor driver is publishing over the network. Just like that. And a quick show of how to generate that Python client is described by this README that I created. So if I go to test client, there is something we can do. First thing we do, we set up an environment, we create a Python environment, we activate that environment, install requirements if they are needed. This is done like this. Requirements are basically the dependencies, your Python packages that you need to run. The packages that we need to run gRPC are only this one, and this one brings the proto C compiler plus the actual gRPC runtime library to be able to call your functions. For example, if we call this Python, I'm gonna erase this for you just to show you. My Python client probably is not gonna work anymore because the generated code, I just erased this to show you how it's gonna be generated. So here we call the module gRPC tools proto C. We tell protogen where to look for the proto file, which is 2 folders above here on this. So it goes up to test and then go back to the root. Then we tell that it generates the Python out at the directory of the protogen. So protogen is the include directory, so it's going to put all the generated files at that folder. And with respect to that folder, it's going to generate the modules. So protogen was fully generated by gRPC just by calling this requirement and by calling that function you are already that quickly being able to call the service that the gRPC server is providing. So just doing that and writing a very simple function like this, open the channel, call the stub, the sensor services stub, which is this sensor services. You create the stub, then you perform the request, and immediately you can have access to the points. Of course, you can also do like this for point in scan.points. You can actually print the individual points. So Python client, yeah, way too many points, but here you see all the actual points being rendered. Some points are empty, invalid points, but what matters is that the data is coming out of my Raspberry Pi, reaching out my edge device, which is emulated by the computer that I'm using right now, the MacBook. But if this could have been written in any other device that has gRPC or other stuff contained. All right, just like this, we call the driver, and the Raspberry Pi is serving the LiDAR as a service to my clients. I just turned off the LiDAR, so this stopped, and I'm gonna comment this out. The driver no longer receives the data. I'm gonna turn the sensor back on, then it starts rendering points over to the network once more. Based on a proto file, it's really simple. That is enough for you to fetch LiDAR data that's provided by another service. That is really cool. But I do not get tired of saying that gRPC is a really cool technology. And like I said at the beginning, ROS is a very nice tool. It solves a lot of really common problems. But what makes me like gRPC sometimes for that kind of particular use cases more is the freedom that we have to choose our language, the languages that we can do stuff on. For example, this is Python, and this is a full-fledged TypeScript application that is running a gRPC client directly accessing the LiDAR sensor that is data that is being published by my driver, just like this, via the web. And you know what's even cooler is that I can do this. This is the same TypeScript application that I'm running in my smartphone via the web that is accessing the LiDAR sensor data published by my C++ application, just like this. And that I think is really cool, and that will be something a little bit more difficult to do with ROS alone. And I could spend a whole day playing with this kind of stuff. And that, my friends, is how you can expose your sensory data as sort of a microservice for any person from different technologies or different backgrounds, different languages to benefit and consume your data from. Thank you very much for watching.